the total number of buildings for the area listed here. Red represents the number of correctly detected buildings, and yellow represents the number of false negatives. And again, you can see the yellow bars are kind of higher for the smaller buildings, but then the yellow proportions of those bars get smaller as the building size starts to increase. And there are quite a few buildings greater than 250 meters squared, but this doesn't fluctuate too much from there on out, but it does fluctuate quite a bit in the beginning for the lower size buildings. So we wind up comparing this method to other methods in the literature. George Wasselman has a method where he was able to realize 85% and 90% completeness and correctness. Matejnikin has a method for 90 and 85% completeness and correctness. And then Rottensteiner has a method, and he was able to receive 87 and 91% completeness and correctness. So you can see that the method is somewhat comparable to the other recent methods in the literature. Some things to point out is methods 2, 3, and 4 actually require that the data set be interpolated. And then methods 2 and 3 rely on both the aerial imagery and the LiDAR data. And they say as part of a pre-processing technique, you have to register the buildings, the LiDAR data to the aerial imagery. This is not a trivial task. This was done manually, unless they, otherwise they would have published for it as automatic registration from LiDAR to aerial imagery is an actively sought-off topic in the academia. The other thing is Rottensteiner, with his method, he has a parameter where in order to get this performance listed in his publication, you have to estimate the amount of vegetation contained within the scene within 5% of the actual ground truth. So there's quite a bit of manual inspection involved in order to fine-tune that parameter. The comparisons against Wasselman and Matejnikin can be viewed as a qualitative comparison because they're actually using different data sets than me, so it's not really fair to directly compare to them. However, the comparison to Rottensteiner is directly applicable in terms of the Fairfield data set because he is using the exact same Fairfield data set for his method. So what have we done here? We wound up proposing a method that works off the irregular LiDAR data. There's no interpolation necessary, whereas a lot of methods will require the data be interpolated, introducing additional processing to accomplish that. There's no overly restricted assumptions being made about the buildings. We don't care the size of the building. As long as the building arguably has a roof, has an area of greater than 40 meters squared, and protrudes from the ground by at least 1.5 meters, which winds up being about 9 feet, I think. The algorithm's a tertiary classifier. We get building, non-building, and vegetation out of it. The ground detection is useful for the application of developing digital terrain models, and it has competitive performance with recent methods, and works off of just the LiDAR data, not requiring additional sources. In my dissertation, I wound up implementing a method, and the dissertation is posted online at nshorter.com. And I wind up saying, okay, now that we've identified the buildings in LiDAR, as Dr. Lael had mentioned, some of the other tasks that I accomplished in my dissertation was automatic building detection from aerial imagery, the registration of the two sources, and then what we actually wound up doing was doing improved detection afterwards. And the system wind up implements a paradigm where you incorporate the information as it is available, which is kind of useful because if you have aerial imagery, we can do building detection. If you have LiDAR, we can do building detection. If you have both, we can automatically register them together and do an improved source of building detection. It comes nice to have that because then as your customer gets more data, you can improve the accuracy. But on the flip side of the coin, that becomes challenging because then it's easier to develop a system that requires both and get better accuracy. The flexibility winds up increasing typically the complexity of the design of the system. More is available, you have to account for. Then if I just have this, I do this. If I get more, how do I improve that beyond that? Harris Corporation actually allowed me to give a couple technical seminars about this work, and they gave us some funding. I'd like to thank them for that, as well as the people who contributed the data. And Dr. Anagnostopoulos, who's a professor out here, actually served on my committee, and I'd like to acknowledge him and thank him for participating in this work as well. But that concludes my talk. Does anybody have any questions? It is a challenge for hilly terrain, yeah. That certainly brings up a good point. If the terrain is hilly, it's not a problem as where the problem I've found, notice the algorithm comes into play as I got in the hand to test it on some other data sets outside of this, is that there's lots of vegetation on the hills. If the hill doesn't have like an exorbitant amount of vegetation, the algorithm will grow up the hill and it'll label the core portions of that hill as being non-ground. Unless the hill is 45 degrees angle steep, then it starts to become a problem and it'll violate certain assumptions there. So when the terrain becomes hilly and succeeds for the urban area shown, it does present a problem for a challenge for the algorithm. Oh, surface and avoid. Yeah. The homotopy tree process, here we wind up exploiting the homotopy trees as a means to represent the relation of wall-connected sets and non-wall-connected sets. And it's nice to have the homotopy tree to represent this relation of these complementary sets. And then because they exist at even and odd generations, we can make the assumption that if a wall-connected set has a child, that corresponds to the building's roof if that's a first-generation connected set. In math, what you'll see is the homotopy trees wind up relating two types of surfaces based on their spatial arrangement and how they're configured. Here, imagine this is like some kind of shape, and these are holes. That's why I said voids, because this is a solid shape, and this is holes within the shape. The same thing here. We have like a polygon shape. There's a rectangular hole in the middle of it, and then you have a circular shape contained inside of that hole. So that's what I meant by void. It's a hole in the shape. I'm sorry, come again? Here, again, you have the holes. It doesn't matter, like this is like a nadir perspective of it, so you don't necessarily take into account the three-dimensionality. This is just a two-dimensional view of the shape. How these shapes are shaped doesn't really matter. With the way we use it in the building detection algorithm, when we actually say